Ever feel like your phone's about to burst into flames when you're gaming? Like the tech's barely keeping up with our thirst for, well, more tech.
Yeah, it's kind of wild, right? All this amazing tech, AI, everything, it's putting a real strain on our electronics. But what if there's a way to, like, supercharge things? Make them faster, way more efficient?
That's what we're diving into today, superconductor electronics. They're not just cool, they're cryogenic cool. Literally.
And to guide us through this super chilled world, we've got Dr. Scott Holmes. He's leading the charge, no pun intended, in figuring out how to actually build the future of computing.
We're going deep on some seriously cool tech, all based on his recent seminar. So, Dr. Holmes, before we get into the nitty-gritty, what are superconductor electronics? Why is everyone so hyped about them?
At their core, superconductors are materials that can conduct electricity with absolutely zero resistance. That means no energy is wasted as heat.
Zero resistance, so like
Yeah.
a phone that charges in seconds.
You're getting the idea. The catch, of course, is that this incredible efficiency only happens at incredibly low temperatures. We're talking a few degrees above absolute zero, colder than outer space.
Okay, so that's where the cryogenic part comes in.
Yeah.
But the payoff is huge, right? Not just for saving energy, but for revolutionizing how powerful our devices can be.
Precisely. We're talking potentially thousands of times faster than today's computers, all while using a fraction of the energy.
Wow. Okay, but how do these superconductor circuits even work? What's going on at that microscopic level? I keep hearing about single flux quantum circuits, SFQ. Sounds kind of like sci-fi to me.
It does have a certain ring to it. Think of SFQ circuits as the backbone of the supercooled world. And the real heroes of the story? Josephson junctions.
Josephson junctions. Okay, now you definitely sound like you're from Star Trek.
Maybe a little, but these are very real and crucial for making this tech work. Imagine two superconductors, right? Now separate them with the thinnest layer of insulation you can imagine. That's your Josephson junction.
Okay, I'm picturing it. Then what?
Here's where it gets truly wild. Pairs of electrons, called Cooper pairs, can actually tunnel through that barrier.
Tunnel. Like quantum tunneling, right out of a physics textbook.
Exactly. And this is how we control the flow of current with incredible precision. Dr. Holmes used a rather interesting analogy. Imagine you're trying to feed a baby.
Okay, this is about to get weird, isn't it?
Perhaps,
Yeah.
but it makes sense. You try to feed a baby too much milk too fast, what happens?
Things get messy.
Exactly. And a Josephson junction is similar. Too much current too fast, and it sort of spits out the energy as a voltage pulse.
So it's like a tiny super cool baby with a milk aversion.
In a way, yes. And those pulses, those are what we use to represent information to make the circuits think.
So it's not just about the junctions themselves, right? There's a whole architecture to these circuits.
Absolutely. We connect them in specific ways, create loops, use something called inductance. It's like a high-stakes puzzle to control those single flux quanta, those little packets of energy.
A puzzle where getting the answer right could revolutionize, well, everything.
Now you're getting it. And that's what leads us to the big question. Which logic family will be the one to make this happen?
A logic family showdown.
Huh.
It's like the Wild West of superconductor circuits out there. But what makes one logic family more killer than the others?
You're hitting on a key point, scalability. We're not talking about shaving a few milliseconds off your internet speed here. We want billions, trillions of these Josephson junctions on a single chip. That's when things get really interesting, really world-changing.
Billions, trillions. Okay, yeah, I see why we need to figure out the killer logic. But more importantly, how do we even power something like that? I can barely keep my phone charged.
That's the million-dollar question, literally. Imagine, right? Traditional superconductor logic, it uses a constant DC current. Now, try sending that much power to billions of junctions. It's just not feasible, like trying to power a city with a watch battery.
Literally not going to work. So what's the alternative? How do we get strategic with this super-powered energy grid?
Think pulses. Instead of a constant flow, we send bursts of energy only where and when it's needed. We call this AC-powered logic.
Okay, so it's all about timing, making sure each junction gets a jolt of power at exactly the right moment. Dr. Holmes mentioned some pretty sci-fi names for these AC-powered contenders.
He did. AQFP, adiabatic quantum flux parametron, kind of rolls off the tongue, right?
Sure, I'll take your word for it.
And then there's SSBF, or superconducting sustainable ballistic fluxon. Bit of a mouthful, but the point is, these offer new ways to send power efficiently, potentially a game changer for getting around the limitations of that constant DC current.
It's like we're choreographing a super fast, super complex dance of energy here. But even with AC power, there's still the issue of, well, space, right? How do we fit all those junctions onto a chip?
Exactly. It's not enough to just power them. We need to make them tiny, pack them in tight. And that's where those inductors we talked about earlier, they start to cause problems. They take up a lot of space.
So it's like trying to fit 1,000 pianos into a one-bedroom apartment. Not going to happen.
Pretty much. So what do we do? Well, we could shrink the pianos or figure out how to live without them.
And in the world of superconductors, that means
Phase engineering.
Okay.
Yeah, it sounds kind of sci-fi, but stay with me.
quantum babies, mill-powered circuits. Trust me, I'm along for the ride.
Remember how those Josephson junctions have a certain phase, a sort of state that determines how those Cooper pairs tunnel through? Well, phase engineering is about manipulating that, fine-tuning it to make circuits smaller, more efficient, without needing those bulky inductors.
So instead of shrinking the pianos, we're getting rid of them altogether and buying, like, a really nice sound system instead.
Exactly. And one way to do this is with something called, wait for it, pi junctions.
Pi,
Yeah.
3.14159. What's math got to do with superconductors?
Believe it or not, it's the same pi, but in this case, it's a special type of Josephson junction. See, in a regular junction, those Cooper pairs, they like to tunnel through when there's no phase difference. But a pi junction, they like it when the phase difference is exactly pi.
So they're like, the daredevils of the electron world got to take the more challenging route.
Love it. And by combining these pi junctions with regular ones, we can, in theory, design circuits that are just inherently more compact, more bang for your buck, or, well, less space for more computing power.
This is all starting to sound too good to be true. Smaller, more efficient, more powerful. There's got to be a catch.
There's always a catch, and in this case, it's manufacturing. These new, improved junctions, they're incredibly difficult to make reliably, especially at the scale we need.
So we have the blueprints for a revolution, but actually building the factory, that's the real challenge.
And that's where things get really exciting, right?
So where are we on the superconductor superhighway? Are we close to ditching our old devices for something straight out of sci-fi? Or is this more of a long game?
If only I had a crystal ball, right? But that's the beauty of these deep dives. We get to peek into the labs, see the blueprints before the buildings are built.
Exactly. And speaking of blueprints, Dr. Holmes spent a good chunk of his talk on something that always gets me hyped, quantum computing. It's like the ultimate what if, you know?
It's definitely a mind bender, but the possibilities, limitless, really. Think problems that would take our best computers like millions of years to crunch through. Quantum computers could, in theory, handle them.
Millions of years compressed into, what, minutes? Hours? Okay, now I'm really listening. But how do we even build something capable of that?
That's the multi-billion-dollar question, and the answer might surprise you. It's our old friend, the superconductor.
Wait, seriously? All this talk about cryogenic temperatures, Josephson junctions? That's all connected to quantum computing, too.
More connected than you might think. In fact, Dr. Holmes and the IRDS team, they're predicting superconductor electronics will be essential for quantum computers, especially as they scale up.
Okay, color me intrigued. Why is that? Why are superconductors so crucial for quantum's big debut?
Well, imagine this. You've got your quantum computer, right? But it relies on these super fragile qubits, quantum bits that only work at crazy low temperatures.
Right, like we talked about earlier. Got to keep things chilly for those electrons to do their thing.
Exactly. Now try controlling millions, billions of these qubits, all at a fraction of a degree above absolute zero. It would take an insane amount of energy, be incredibly inefficient, and let's be honest, probably melt your motherboard, unless you bring the control circuits down to the qubits level.
Enter superconductors. It's like building an express lane straight to those qubits.
Exactly. Suddenly, communication is fast, efficient, and potentially scalable. No more traffic jams on the quantum superhighway.
Okay, you've sold me superconductors. They're the key. But let's talk reality check. What needs to happen, like really happen, for all this potential to become, well, reality?
The million-dollar question, part 2, it all comes down to this.
Yeah.
Can we make enough of these incredibly complex circuits reliably without breaking the bank? And the answer, at least for now, is not quite.
So we're back to those manufacturing hurdles. Scaling up, pushing the boundaries of what's possible. It's like we're trying to build a spaceship while the engines are still being invented.
A very expensive, very delicate spaceship. But that's the thrill of it all, isn't it? This catching the wave Dr. Holmes talked about, being ready for that moment when a breakthrough changes everything.
And in the meantime, we get to watch those waves build, see the future of computing take shape, one super-cooled, mind-bending discovery at a time.
And that's a future worth getting excited about.